For much of modern history, the most widely accepted explanation for the origin of the universe has been the Big Bang theory. According to this model, all matter and energy in the cosmos originated from an unimaginably dense and hot state. This intense eruption triggered an ongoing expansion that ultimately gave rise to atoms, stars, galaxies, and all known structures. It has served as a foundational pillar in the field of cosmology for generations. But recent research has begun to cast doubt on the notion of a single, definitive beginning. A number of cosmologists now propose that the universe may be part of a greater, repeating cycle. In this model, the cosmos doesn't begin and end with one explosive event, but rather moves through a sequence of expansions and contractions, over and over again. The concept introduces a radically different vision of the universe, not one that is born once, but one that is continuously reborn. Prominent physicist Brian Cox is among those who have questioned the validity of the Big Bang as the absolute beginning of everything. He has voiced skepticism about the possibility that the universe could emerge from complete nothingness. His perspective reflects a broader intellectual movement in physics that is seeking to reevaluate long-standing beliefs about cosmic origins and ultimate boundaries. Fueling this paradigm shift are observations from the James Webb Space Telescope, JWST. Data from this groundbreaking instrument have revealed that some galaxies seem to have formed far earlier than our current models would predict. These ancient galactic structures challenge the idea that the Big Bang marked the true start of the universe, raising a compelling question. If the Big Bang wasn't the first event, what preceded it? To begin unpacking this mystery, scientists are delving into the earliest moments accessible through observation and theory. As new discoveries are made and old ideas are re-examined, our understanding of the universe continues to evolve. This journey isn't just a technical investigation. It is a profound exploration of our very existence and its possible continuity through time. The Big Bang theory still remains the most popular and evidence-supported framework for explaining the universe's infancy. According to this model, around 13.8 billion years ago, the cosmos existed as a tiny, searingly hot, and incredibly dense point. Within moments, subatomic particles coalesced to form simple elements, setting off a chain of events that would eventually lead to the formation of galaxies, stars, and planets. This model suggests that the universe started from a minuscule point, smaller than an atom, and expanded rapidly. Key evidence supporting this includes cosmic microwave background radiation and the observed distribution of elements throughout the universe. These observations offer compelling signs that such a dramatic expansion event likely occurred. Despite its strengths, the Big Bang theory is not without its shortcomings. It struggles to account for the conditions during the universe's earliest fractions of a second. Our most sophisticated tools in theoretical physics, such as general relativity and quantum mechanics, begin to falter under these extreme conditions. Near the singularity, a proposed point of infinite density, our equations no longer yield reliable answers. At the center of this problem is the singularity itself, a theoretical point where the fabric of space and time becomes infinitely curved and the laws of physics break down. The idea that all of existence emerged from such a state is difficult to reconcile with our current scientific understanding. To transcend these limitations, scientists are exploring new models that might better describe the universe's behavior in its most extreme early stages. One such model comes from string theory, which attempts to unify all fundamental forces, including gravity. In this theoretical framework, a concept known as the ekpyrotic universe has taken shape. The term ekpyrotic, derived from an ancient Greek word for conflagration, implies that the Big Bang may not have been an origin event, but rather a transition from a prior cosmic state. This perspective leads into the broader realm of cyclic cosmology, which holds that the universe perpetually cycles through expansion and contraction phases. Cyclic cosmology has roots in both ancient philosophy and modern theoretical physics. It presents the universe as an eternal loop, oscillating between periods of explosive growth and eventual collapse. One influential figure in this area is Sir Roger Penrose, a Nobel Prize-winning physicist who developed a model known as conformal cyclic cosmology, CCC. Penrose's CCC suggests that the future end state of one universe, a vast, cold, and empty expanse dominated by low-energy photons, can resemble the highly compressed conditions associated with a new Big Bang. Over time, as black holes evaporate and matter decays, only radiation remains. At this point, because all particles are traveling at the speed of light, the universe loses any meaningful concept of size or time. Through a mathematical procedure called conformal transformation, this infinitely stretched state can be reshaped into a new beginning. The end of one cosmological phase becomes the genesis of the next. In this way, time, as we understand it, becomes a circular continuum rather than a straight line. This interpretation upends traditional views of time and causality. In our everyday understanding, time progresses linearly from past to future. But under the CCC model, the end of one universe and the beginning of another are not sequential moments, but rather different expressions of the same eternal process. The implications of this are staggering. If time dissolves or resets at the boundaries of cosmic transitions, then our concepts of beginning and end lose their conventional meanings. For an observer at the end of a universe, existence might appear static or final. Yet, from another frame of reference, that very state could signal the emergence of a new universe. Likewise, the early universe, boiling with energy in the wake of the Big Bang, would offer no indication of a preceding cycle. To observers within that state, the cosmos would seem fresh and without precedent. The absence of memory or continuity between cycles emphasizes the separateness of each phase. Penrose refers to these distinct cosmic phases as eons. Each aeon unfolds according to its own rules and timeline, yet is connected to the next through conformal transitions. This idea challenges our deepest philosophical intuitions, suggesting that there is no absolute beginning or end, only transformation. The ramifications extend beyond physics into the realm of metaphysics and philosophy. If the universe is eternally self-renewing, then the need for a first cause, a common argument in both science and theology, is obviated. Existence, in this view, is a perpetual motion machine, with no origin and no terminus. Some researchers suggest that quantum fluctuations might leave subtle imprints on each subsequent aeon. These quantum traces, encoded in the cosmic microwave background, could serve as empirical evidence for earlier universes. Penrose has proposed that circular patterns in this ancient radiation might support his model. Quantum mechanics plays a fundamental and transformative role in modern cosmological theories, especially those involving cyclic models of the universe. At its core, quantum mechanics challenges the deterministic worldview of classical physics by introducing the concept of probabilistic outcomes. In this framework, particles can exist in multiple states at once, a condition known as superposition, until they are measured or observed. This phenomenon means that, at the most basic level, reality is not fixed but fluid, governed by probabilities rather than certainties. When this principle is extrapolated to the scale of the entire cosmos, its implications become even more intriguing. If the universe itself is subject to quantum uncertainty, then each new cycle, or aeon, as Sir Roger Penrose refers to them, may begin under slightly different initial conditions than the previous one. These subtle variations could arise from quantum fluctuations occurring near the end of the previous universe or at the moment of transition between eons. Over time, these minor differences might accumulate, leading to meaningful variations in how physical laws manifest or how cosmic structures form in each cycle. This idea introduces a compelling twist to the concept of an eternal, repeating universe. Rather than envisioning a perfectly identical loop playing over and over like a cosmic movie on repeat, quantum mechanics suggests a universe that rewrites itself each time it is reborn. Every cycle may be governed by the same underlying principles, but quantum randomness ensures that no two eons are precisely the same. Stars, galaxies, and even the fundamental constants of physics could vary slightly from one cosmic iteration to the next, creating an infinite tapestry of diverse universes. Furthermore, Penrose and other researchers have speculated that remnants or echoes of previous cycles might still be observable today. These might appear as faint, circular patterns, or anomalies in the cosmic microwave background, the residual heat left over from the early universe. If detected and verified, such features could provide tangible evidence for cyclic cosmology and quantum influence on the large-scale structure of the cosmos. In essence, quantum mechanics doesn't just shape our understanding of the subatomic world. It reshapes our understanding of time, existence, and the very fabric of the universe itself. It hints at a cosmos that is not only eternal, but also richly dynamic, forever shaped by the interplay between probability and cosmic scale. Several models attempt to explain how these cycles function. Some propose a universe that loops endlessly with no initial impetus. Others speculate that a deeper, underlying reality, possibly governed by yet undiscovered laws, dictates the structure and rhythm of these cycles. In some interpretations, the end of one phase determines the beginning of the next, closing the loop. Despite differing approaches, a unifying idea persists. The cosmos is not defined by a single, unique origin. Instead, it is a dynamic and recursive system that transcends the constraints of linear time. This shift in perspective challenges our current scientific framework and invites a re-examination of long-standing assumptions. The Big Bang Theory, while powerful and predictive, may not encompass the entire scope of cosmic history. It successfully describes a moment in time when the universe transitioned into its current expansive state, but falls short of explaining what came before or what might come after. In contrast, cyclic cosmology presents an alluring alternative. It provides potential solutions to long-standing paradoxes, such as the nature of singularities and the arrow of time. It also seems to align with new astronomical data suggesting that structure and complexity in the universe may have emerged sooner than the Big Bang model allows. This vision of the cosmos as a never-ending sequence of creation and destruction not only expands our scientific understanding, but also deepens our philosophical insights. It compels us to rethink fundamental concepts such as time, causality, and existence. In all these views, one idea remains central: that the cosmos is far more complex and mysterious than a single explosive event. Whether or not cyclic cosmology eventually replaces the Big Bang Theory, it offers a compelling alternative that aligns with new observations and addresses old paradoxes. Ultimately, the notion of a cyclic universe encourages us to transcend traditional boundaries. It pushes science into bold, new territory, where the edges of physics blur into philosophy. As technological advancements like the James Webb Space Telescope continue to gather data, we may find ourselves standing at the brink of a scientific revolution. Perhaps the cosmos is not a one-time miracle, but an eternal dance of energy and form. In this vision, there are no final answers, only endless transformations. The search to understand our universe becomes not just a quest for knowledge, but a journey into the heart of existence itself. Whether the universe ends in fire, ice, or another mysterious rebirth, one thing becomes increasingly clear: the story of the cosmos may never truly end.